Hello, my name is Andrew Stallard. This is the first video on my series on APC, Physics, Electricity, and Magnetism. Today we're going to talk about Coulomb's law. So without further ado, let's start. The Coulomb force, or the electric force, or the electrostatic force, Fe, follows this formula. K, the Coulomb constant, Q1 and Q2 are charges. Point charges for this formula. Any electric charge located at a point, and their units are in coulombs, just like the name of the law, named for the man who discovered it. And R is the distance between them. And since this is a force, it is a vector quantity, it is in the direction, that force is in the direction of that distance. K is 8.99 times 10 to the 9 MKS units, and it comes from another constant, the permittivity of free space, and that's 8.854 times 10 to the negative 12 in MKS units. Notice this is similar to the gravitational force, and that they are both inverse square laws. And this also is, of course, in the direction, the distance, in the direction, and goes in the direction of the two bodies. Now, what are the units of this K? We know that the units of force are newtons. And the units of charges are coulombs. And in MKS, the units of distance are, of course, meters. Both these charges, so this is the force newton is going to have units of K times Coulomb squared over meter squared. So K is going to have units of Newton meter squared per Coulomb squared. Not Coulomb seconds, Coulomb squared. And one more important thing about force between charges, both charges are both positive or both negative, that force is repulsive. If one is positive and one is negative, that force is attractive. Now let's say we have two 1 kilogram spheres, each carry a charge of magnitude of 1 coulomb. How does this Fe, the strength of the electric force between the spheres, compare to Fg, the strength of their gravitational attraction? So we need to find Fe over Fg. Now Fe is still K, Q1, Q2, over R squared, and Fg is still G, M1, M2, over R squared. Q1 and Q2 are both 1 coulomb. 1 times 1 is 1. That's redundant. M1 and M2 are both 1 kilogram. 1 times 1. That's also redundant. So we divide these, the R squareds cancel out. This is the same in both cases. So that's just going to be K over G. 8.99 times 10 to the 9 over G, which is 6.67, times 10 to the negative 11. And MKS units, if you remember that. So, this ratio is going to be 1.34 times 10 to the 20. The electric force is much stronger than the gravitational force. And this is something of an underestimate if you use subatomic particles. If you did this with a proton and electron, you would get something like 10 to the 45. But since there is only one kind of mass and two kinds of charges, it is gravity that determines the large-scale structure and evolution of the universe. Let's do some problems. Two charges, one of 5.46 microcoulombs and the other of negative 6.47 microcoulombs, are separated by 10.2 centimeters. What's the force between them? Let's do and B. Is it attractive or repulsive? Since these two charges are opposite, one's positive, one's negative, it's obviously attractive. So we have Q1 here, Q2 here, and we have a line between them. Okay? And this is going to be R, 10.2 centimeters, sorry about this, I have terrible writing, terrible handwriting. Microcoulombs. So let's do this. Our force, K, times 10 to the 9 times 5 point, we're going to write this, change this microcoulombs to coulombs to keep the units consistent with this K, with the K. All over R. Now we have to change centimeters to meters, again, to keep the units consistent. Oh, 102 squared. Now when you put this in your calculator, you're going to get 30.53 newtons. 3053 newtons. That's just the 4 sig figures. We're using an extra one because we're going to continue to use this in calculation. Look at part C. If the 5.46 microcoulomb charge is a mass of 284 grams, it's released. Okay, what's its acceleration? So let's say the one charge gets released and it's going to accelerate towards the other. So we have Newton's second law here. F is ma. A is F over m. This is 3053 newtons over the mass, which is in kilograms. It's got to be in kilograms. We're going to change that those grams to kilograms, 0.284 kilograms. And then the units, the answer in the units are 10,700 meters per second squared. Now, looking at this second one, this is going to be a little trickier. We have two dimensions, and we know that force is a vector quantity. So we need to take into account both the x and y components of this force. So let's start by getting our Cartesian plane here. I'm going to draw an x-axis, a y-axis, and an x-axis here. And this is going to be y, and this is going to be x. And we have a charge at the origin that's 2 microcoulombs. Two microcoulombs at the origin, then we have 3, I'll write that here so you can see. 2.00 UC. We have a charge at 3, 4. 1, 2, 3, 4. That is negative 1.87. Microcoulombs. And we have a charge here at 2, negative 3 of 4.23 microcoulombs. Now, we define the force on the origin. We have a negative charge here and a positive charge at the origin. Is the force going to be going towards the origin or away from it? It's attractive, so it's going away from it. This negative 1.87 microcoulomb charge is pulling this up this way. Now, but what about this one? Is this going towards the origin or away from it? This 4.23 is repulsive. It's pushing away at this charge on the origin. So the forces look kind of like this. Now, these can be resolved into x components and y components, and that's what we have to do to add them. Here and here. So we start out with our Coulomb force law. Heck. Just dashes F. K, Q1, Q2 over R squared. In the R hat direction. But what's that going to be? For the first one, let's call this angle theta. Let's call this angle alpha. So this one is going to be, for the negative 1.87 charge, it's going to be cosine of alpha, R hat, is cosine alpha, or cosine theta, x hat, plus sine theta y hat. Cosine of theta is, cosine is adjacent over hypotenuse, so that's going to be 3, and if we have 3 and 4 here, that's a simple Pythagorean identity. The distance, the actual distance between the origin and that point where the negative 1.87 charge is 5. So cosine theta is going to be 3/5 x hat plus 4/5 sine is opposite over hypotenuse, y hat. Now, for this other one, the other R hat, okay, call it R2 hat to distinguish it. Now, this is going, notice that this vector is negative. in the x direction. That's going to be negative cosine alpha x hat plus sine alpha y hat. Okay? Now cosine alpha, cosine is adjacent over hypotenuse. The adjacent is 2, and the hypotenuse, by Pythagorean theorem, is square root of 2 squared over 3 squared, that's root 13. And again, sine, that's going to be 3 over root 13. Now, putting these numbers in, we have k. Okay, I'm going to get rid of this. Mine, I'm going to erase some of this here. F1 for this is going to be 8.99 times 10 to the 9 times negative 1.87 times 10 to the negative 6 times 2 times 10 to the negative 6, yes, I know, over this distance, which is going to be 5 centimeters, 0.05 squared. I'm going to take this and multiply this by 3/5 x hat plus 4/5 y hat. X hat, y hat, unit vectors in the x and y direction. So when we do that, put that in your calculator. We get 8 point, or computer algebra system, 069 x hat plus 10.76 y hat. Because this, again, it's a force. It is a vector. It has components. Now let's look at the second force. That one again, it's still K, which is 8.99 10 to the 9 4.23 times 10 to the negative 6 times 2 to the negative 6. all over radius squared. We know that the radius is the square root of 13 centimeters. So we can just, it's going to be the square root of 13 times 10 to the negative 2. So doing this a little arithmetic, this is the square root of 13 times 10 to the negative 2 meters. So if we square this, we have 13 times 10 to the negative 4. Again, that's a Pythagorean identity. Now, we have negative 2. We're going to multiply this by negative 2 root 13 x hat plus 3 over root 13 y hat. And we get negative 24 0.38 x hat plus 59.44 y hat. Just put that in your calculator or your computer algebra system. It looks hard, but it really isn't, okay? It is involved. That's the force. The magnitude is a Pythagorean identity. It's going to be the square root of this term squared plus this term squared. Again, it's a force. It's not exactly these vectors, since these vectors are really displacement. You can't just add these two, but force is a vector. It can be resolved to components. Its magnitude is a Pythagorean identity. And we get 64.2 newtons. And its direction is the arctangent Now you have to be careful with the arctangent if you remember your trig. If you're putting in the calculator at least, I like to just make the angles always positive and then think about where they are. Okay? When we plug this in, okay, we're going to get an answer of around 67 degrees. But 67 degrees from what? This is negative in the x and positive in the y. So it's going to be 67 degrees above the negative x-axis. If we have a circle, the angle that we're looking for is going to be here. If it's negative in the x and positive in the y. Now that was really involved, but it is doable. And we're going to introduce next time the concept called a field, which might make this a little easier. Moving on. But right now, let's end with this. What will happen to the magnitude of the electric force between two particles if the distance between them is double and the charge is tripled? Okay. So if we look here, we have F is K Q1 Q2 over R squared, and F2 and each is going to be 3Q1 times 3Q2 over 2R squared. Now let's look at this. F2 over F1, and there's a K here too. F2 over F1, 3 times 3 is 9, 2 squared is 4. So F2, if we triple both of the charges and double the distance, F2 will be 9/4 of F. I hope that was useful to you. Thank you very much, and hopefully I will have the next video on fields out shortly. Thank you for listening.